All right, welcome to section 8.3. And in this section, we're going to be looking at something called a population proportion. We have some new formulas, but it's going to relate to our previous two lessons. I think this is best shown by looking at an example problem. So suppose we look at a city or a town, and we sample 500 people, and we find out that 421 of them, so kind of old data because now it's almost everybody, but back then 421 people had a cell phone. So 84% of the people have a phone. We want to use a 95% confidence interval or confidence level to create a confidence interval that would say of the whole city, we are 95% sure that between this percent and this percent have a cell phone. So we know of the group we sampled, 84.2% have a phone. So we would need to subtract a little bit from that and add a little bit to that. And we would be able to say 95% of the people fall within that range. And we'll go ahead and calculate that in a bit. But I first of all want to kind of demonstrate how this turns into a normal distribution. So let me remind you about our normal distribution curve. Remember, this is dropping balls through this kind of Plinko simulation. And this is a 50-50 chance. We could let this go on forever. And we have these blue bars showing where it should be and the red bars showing where it happens to occur. And I can reset that. So for our problem, what was it? You can change the probability, see how it tilts the little sticks here. So as we tilt it, see how they're going to shift more to the right, right? So that would be people yes to a cell phone. So all the way down here, that'd be all 12 people have a phone. We can drop some balls there, and right. So I mean, most of the time, you're going to get out of 12 people, you'll get like 10 people that have a phone, something like that. But we could go and take this into the future, and we can see how this creates kind of a skewed normal distribution, but it still looks like a standard normal distribution. I can kind of show something like this. Here you can see how at a 63%, you can see more of that normal distribution. And if I pause that, I can just drag these probabilities around, and you can see how as I change the probabilities, our normal just right, it gets really goofy at like 0 chance of happening, because that just that's not very fun, right? We can watch that one. They all just go to that side. So it gets the shape looks a little bit goofy on the ends, but it still does make a normal distribution. Just a lot end up getting caught in that first column. Okay, so regardless of what our probability is, we still have a normal distribution. That's kind of the point of this introduction. All right, so let's take that, go back to calculations. We're going to calculate what's called the population proportion, and we always use these formulas whenever we have that binomial situation. Whenever we have a chance of something happening, remember probabilities are between 0 and 1, so we have a chance of something happening, and then we have a sample, a town that we're picking from or a classroom, then we're going to use this binomial distribution, or we're going to use a binomial population proportion, which will relate back to our normal distribution. So earlier in the class, we talked about a binomial distribution. And remember on here, we had n, which was how many trials we were doing, or how many people we were picking from. And p was the probability of success. And down here, we're going to have something called p hat. And p hat is going to be the probability of success also. So another way to calculate the probability of success, it's just the number of successes we have. So x is the number of successes, and n is the total number. So like for our cell phone problem, 421 over 500. We'll generally already give you that probability of success as a decimal, so don't get too worried about that. This here is going to show that this is going to be approximately represented with a normal distribution. And here's a way to calculate our average. If you remember back to our expected value, number of items multiplied by the probability of success. And then here's our standard deviation. So for like our cell phone problem, it was 500 times 0.842. So what, 421 was the average amount of people with a cell phone. We're going to find a way to make this much easier. So don't worry too much about these formulas here. I know that the formulas look a little bit confusing right here, but this next slide is going to summarize it very well for us. So on the bottom of this page, they talk about how they do some algebra. They divide by that n, and they're able to simplify this. So this is called p hat or p prime. So our distribution is going to be a normal distribution with p, which is our chance for success. And then we're going to have our standard deviation over here of p, q, n. Q is just the chance for failure. P is chance for success. N is the total number of trials or number of people we're picking from. And so to create our confidence interval, we're going to take our p hat, our probability of success, and we're going to subtract that error-bound proportion. Very similar to the error-bound mean, the EBM, that we looked at last time. And then we add it. And then we get our range of values, and we'll be able to say we have a 95% chance that the values will be between here and here. So once again, to find your p hat, that's just the chance for success. All the successes over the total. So like for our cell phone one, 0.842. So p hat, or p prime, estimated proportion of success. X is just the number of successes, n is the sample size. And then to find that EBP, that's where we take that z-score again, because remember we are using that normal distribution curve. Then our value over here, so we're going to get that z-score. Then we're going to multiply it by that standard deviation. And so to do that, we're going to have p prime and q prime. So p prime is the chance for success. Q prime is going to be 1 minus the chance for success. So that's just the complement. So if we suppose our chance for success was 60%, Q prime would be the opposite of that, so 40%. So 0.4. Then we divide by the number of trials and square root it. And then we take all that, and then we get our EBP. We subtract that, add that, and that's our confidence interval. So this page has really everything you need. Okay. We don't even really need to get into this. This is just kind of summarizing it, talking about how to manually calculate that z-score. We're going to use a calculator for it. All right, so let's go back to our example. So we're looking at a city, and we're going to look at 500 people. 421 people have a phone. So first thing we do is we calculate the chance people, or the chance for success. So we take all the successes over the total. So 421 over 500, 0.842. That's going to be very important. That's our chance for success. And we want to find a 95% confidence level for the whole city. So we want to be able to say that between 70 and 90% of the people, we're 95% sure between 70 and 90% of the people have a phone. So to do this, we calculated our probability of success, 0.842. That's going to be really crucial. That's what's going to build our confidence level. So we're going to take that 0.842 and subtract something to it, so add something to it, and that's going to give us our range of numbers. So we need to calculate the EBP. So I'm reminding you, I'm going back here. So I just found that P prime, the chance for success. Now we need to find the EBP. So to find the EBP, we look at first of all, the z-score. And to get the z-score, we're going to go to our inverse normal distribution calculator. And we're looking at an area of 95%. So I type in 0.95. And we don't want above or below, we want between, because we want 95% to be in the middle. So it's going to tell us we're going to go out to minus 1.96 and then plus 1.96. So this 1.96 is going to be crucial. That's going to be the number we're going to use for this problem. So 1.96, that's how many standard deviations. We look to the left and to the right. Then we need to calculate the standard deviation. So to do that, we take the square root. of the chance for success, 0.842. The chance for failure, that's just the opposite of 0.842. So 1 minus 0.842, 0.158. Then we just simply divide by the number of people in our first sample, 500, and we calculate all of that to be 0.032. And that's our EBP. So we take that number, we subtract it from the chance for success, we add it to the chance for success, and we get our range, 0.81, 0.874. So we would say we have of the whole city, we're 95% sure that between 81 and 87.4% of the people have a cell phone. And the next slide is kind of talking about that. So we say with a 95% confidence level, 81 and 87.4% of all residents have cell phones. Here's how to do it on the calculator. Part is, oops, checking our answer here. So there is another calculator here where you can type in the favorable cases, the sample size, and the confidence level. And it will go through and calculate this for you. And it will calculate your confidence level. So that's a way to check your work with showing it. And then here's another calculator also. Sample size, number in the sample with the result, and confidence level. This one doesn't show all the work, but it does let you check your work right there. So there's some calculators we can use as well to help us. All right, so that is our video on the population proportion. Remember, we use this when we have a chance of something happening as a percent. And remember, it relates back to this Plinko example where we look and see those normal distributions. And that's it for this video. All right, thanks.